Homework 2 is now posted, and in Homework 2 you're going to set up Kerbal Space Program, get the mods set up so that we can use it as a robotics simulator, and then you're supposed to launch a particular rocket into space efficiently. And not just into space, but into a circular orbit. So let me talk a little bit about what that means in Kerbal Space Program. Kerbal Space Program, you start off with your rocket on a planet called Kerbin. There's your rocket, it's pointing up, and I don't know what planets look like. There's a planet. When we launch the rocket, it's going to ignite the rocket engines, and the rocket engines are going to generate hot gas that goes down, and then according to Newton's laws of physics, if we have something going down, we're going to have a force in the opposite direction, and that's going to push the rocket forward. Now, what we want to do in order to get into orbit is we need to get the rocket from being on the ground, standing still. We need to get it up into space, going sideways. Because if it's in space, outside of the atmosphere, so we've got an atmosphere on this planet, inside the atmosphere, if the rocket is moving, it's going to experience drag against the atmosphere, which will slow it down, eventually causing it to crash. That's not what we want from our rocket. We want it to go up into space, and we want it to be there forever. In a Kerbal Space Program, it is conceptually there forever because the atmosphere stops. On Earth, the atmosphere sort of slowly diminishes towards zero, but at a certain point we can call it zero, but it doesn't really go to zero, and there's not a boundary. But if we can get the rocket into space above the atmosphere, then it's no longer experiencing drag. And if we can make it go fast enough sideways, then as the gravity of the planet is pulling the rocket down, and the sort of momentum of the rocket going quickly is making it go forward, the result will be a circular orbit around the planet. It tries to fall down, it's going so fast sideways that it misses. So in order to get the rocket from being on the ground into space, we have to do two things. And if we were going to launch a rocket in the simplest possible way, we would do these two things in order. The first thing is we need to launch the rocket up. We need to get it up high enough that it's out of the atmosphere. So in Kerbal Space Program, the height of the atmosphere is 70 kilometers. So we would ignite our rocket engines and let the rocket engines burn, pushing the rocket up until our apoapsis, or the expected point on the rocket's trajectory where its altitude will be highest, is above 70 kilometers. And then we can turn our rocket engines off and go ahead and coast. And we probably want to make it relatively, significantly above 70 kilometers, maybe 100 or 120 kilometers, because we want some time while we're up there. We don't just want to peak out above the atmosphere and then immediately fall back down into the atmosphere, because then we're in the atmosphere again. So we'll burn until our apoapsis is at 150 kilometers. Well outside of the atmosphere. And then we shut off the engines and we wait for the rocket to coast. It's going to slow down as it's going up. And then when it gets to 150 kilometers, it would stop. And then it would start falling straight back down. We don't want it to stop and fall straight back down. So around when we get to 140 kilometers, we're going to find a way to turn the rocket sideways. Turning the rocket sideways is tricky in the real world. In Kerbal Space Program, there are, if you just try to turn a rocket, it frequently does turn sideways depending on what actuators it has. The key actuator that lets you turn sideways in Kerbal Space Program is something called a reaction wheel that's based off turning a gyroscope. And that works in the real world. It doesn't work nearly as well as it works in Kerbal Space Program, but that's fine. We'll use our reaction wheels to turn the rocket sideways, and we get up to, say, 140,000 kilometers. We're going to turn the rocket engines back on and start burning right. Right in the diagram. Probably we would want to say east, although probably an even more useful thing to say would be we want to go counterclockwise around the equator when viewed looking down on the North Pole. We're looking down on the North Pole, we're going to go counterclockwise, so that's like a positive rotation in a sort of standard engineering coordinate system. Here, I guess in the picture, we are looking up from the South Pole is what's going on? Yeah, we're looking at this rocket up from the South Pole. I don't know why I drew it that way. But we get up to close to our apoapsis, we start burning, and we're going to burn until our periapsis. So we have this circle that is our predicted orbit, and we're going to burn until the side on the predicted point on the other side of the orbit is also 150 kilometers. And if we did everything right in the process, our apoapsis should have stayed about 150 kilometers. And when both the highest and lowest point that we're going to be at in our orbit are about the same, then we're in a circular orbit, and we've succeeded. There's one sort of trick here, and that is we don't know actually exactly when we have to start that burn, the circularization burn. We want to start burning halfway, we want to start burning such that when we get to apoapsis, we will have half of our burn remaining to do. We want the time on either side of the apoapsis of the burn to be equal. And that will tend to make everything even out, so we end up in a circular orbit. And if we want to actually calculate that, we would have to do arithmetic. We're going to have to do some arithmetic in this class, but it turns out that as we try to make things a little bit more efficient than just launching straight up, we also reduce the amount of problem we have with having to calculate exactly what we're doing with that circularization burn. So the problem with launching straight up is that one of the things that causes inefficiency is us spending time fighting gravity. If we're burning straight up, then however much force we are exerting to try to increase our speed up is being directly countered by the 10 meters per second down of gravity. And so whatever we're doing, we just get to subtract 10 meters per second as far as what benefit we're getting. And that's just a constant decrease on the efficiency of our stuff. We're burning fuel just to stay up, to not fall down, not to go up. So the sooner we can start burning sideways, the less time we have to spend burning up. And also, the lower we can make our goal apoapsis. If we burn straight up, and when we start doing our circularization burn, we have 0 horizontal velocity, then we have to get all our horizontal velocity up in space. If we start burning a little lower, and maybe try to do a curve, we can start to get some horizontal velocity as we're still climbing. The other thing that's a factor is that if we're going sideways through the atmosphere, our rocket will generate a little bit of lift as it's going over air. The air will actually push it up. And that's not a large effect, but we get none of that benefit if we're just going straight up. We have to be going sideways to benefit from any lift. And Kerbal Space Program does simulate some aerodynamics, although not very well. And it may be not very well in our favor. It makes things generate lift that might not generate anywhere near that much lift. So what we're looking at trying to do here is try to figure out what curve do we want to do, how much do we want to tip the rocket over as we go up in order to get an efficient launch. And one way to do that is just have some function, f of alt equals tip over factor. So we have a function of altitude that's going to produce what angle we want the rocket to be at. And in KOS, which is what we're going to be using to actually actuate our rocket, we can straight up set what we want our target tilt angle to be. That's one of the the angles of the rocket, and so we can request an angle, and the rocket will try to get to that angle for us. One sort of really simple solution here would be to make this function be, I can never remember whether I want sine or cosine. I'm not going to look it up. If I'm getting my sine and cosine backwards, people who actually know math, let me know. But if we make this be alt over 100,000, then if I got my sine and cosine correct, then, wait, am I backwards? Do I want arc sine here? Probably. Remembering that I don't know trigonometry off the top of my head at all, I still am able to get rockets to launch. But this is going to be alt equals 0, the rocket is pointing straight up, and then when alt is 100k, the rocket's going to be pointing straight sideways. And that'll give us a nice sine curve that we're turning on. It's not going to be quite this like quarter of a circle curve that I drew there, but it's pretty similar. And yeah, that's one possibility, and that might give you a reasonably efficient launch. It might not, depending on how quickly you're burning. You may have gotten to orbital velocity when you get to 100,000 kilometers. You may have more burn to do. You may also find yourself here with an apoapsis of 100,000 kilometers, and at that point, you burned up too fast compared to your curve. So it's worth spending some effort thinking about whether it's worth doing the math. And I'd recommend trying it and see what behavior you actually get before spending a bunch of time trying to optimize the equations for how to get exactly the right answer for matching a specific curve, because there's a lot of considerations and you don't necessarily have the problems that you think you do until you've tried it. But I think that's the stuff I wanted to draw on a whiteboard before homework 2, so good luck playing around with launching a rocket.